Welcome to our discussion on limits. In order to find these tangent lines, these equations of tangent lines, and just tangent lines in general, we have to kind of buy into this concept of a limit. We have to be able to start with a secant line, so have 2 points on a curve, and then let one point get really close to the other one, but not actually be right on top of it. Otherwise, you still can't compute slope because you don't have 2 points. So we really do need the idea of a limit to even understand how a tangent curve can be calculated. So tangent curves are going to become, limits are going to become very important for us to figure out velocities, accelerations, tangents, all these types of things. So make sure that you understand the idea of a limit. We can start by investigating a very basic function, a function that you should be fairly familiar with, a simple quadratic of x squared minus x plus 2. And then we're going to ask ourselves what happens as values get really close to 2. We're not concerned what happens at 2, right? We're not asking the question, what is f of 2? That's a different question. I mean, we can calculate f of 2 for this particular function, but we don't have to be able to do this, right? Not all functions will be defined at this number that we're going to take limits, close to. This particular case, we can do f of 2, and we can see we get 4 minus 2 plus 2, and we get 4. Okay? But we don't have to have that situation in order to still calculate a limit, because we're not asking the question what happens at 2, we're asking the question what happens as we get really super close to 2. Okay, so we can look at it numerically, which means doing a lot of tedious math of plugging these numbers into the function and getting an answer. When you plug in 1, you get 2, 3, you get 8, so on and so forth. You can see that as these numbers approach 2 from below, right? They're getting closer and closer to 2 from below. The answers are getting closer and closer to 4. And then as we approach 2 from above, right? We started at a bigger number, 3, and we're getting closer and closer to, those numbers also approach 4. So we're approaching 4 from both directions. And if we look at it graphically, we can see that what's happening is as we come in, right, from numbers below 2, the values of the function are increasing up to this height of 4. And as we come down the number line from values greater than 2, the function is coming down to a value of 4. Now, it doesn't, this is an increasing function. So as the x increases, the y increases. As the x decreases, the y decreases. That doesn't always have to be the case, right? We've seen plenty of functions that aren't increasing functions. So don't get caught up in that minutia. The idea is just as you let the x values get closer and closer to 2 from either side, the function values are getting closer and closer to some number from both sides, in this case 4. Okay, so that's basically what a limit is doing. It's saying, how do we get really close to a number? How does x, when x gets really super close to something, do the values of our function always consistently get closer and closer to some other number? Here's the textbook definition. Take the limit as x approaches a of some function f of x, and we say that it equals L. Right, so the limit of the function equals L as x approaches a, and that's only true if we can take values of f of x super close to L, as close as L as we want to, and we can always find values super close to a on either side that are still within that range. That's how we would basically prove that a limit exists. We're not going to do that here. That's a later exercise. Okay, there's an alternative notation for this, that you just say f of x approaches L with an arrow, right, as x approaches a. Not as common. This is the most common way of writing a limit. So get in the habit of writing it this way. Remember, we don't care what happens at a. We do not have x equaling a. In fact, by definition, if you go back up here, you'll notice that it explicitly says not equal to a. So the definition of limit actually says we're not going to let x equal a. We're just going to let it get really super close to it. And that's important because there are going to be instances where we're going to have a function that is not defined at a. F of a just doesn't exist, but we can figure out what the function is doing as x gets really close to a. So that's really all that we're concerned with, is what happens when we get really close, right? Really near a. All right, here's three pictures that'll help kind of illustrate this point of why we don't care what happens at the function. So down below we have kind of the same function written three ways. If you look closely, you'll see that there are slight differences to each of these three graphs, right? It looks like the same curve, and it is the same curve, but a different thing is happening at a for each of them. In the first version, here on the left, f of a exists, right? If we actually evaluate the function at f of a, it's going to equal L. However, if you come over here and look at the one in the middle, f of a does also exist, but it doesn't equal L. It equals something else. It's hard to see, but there's a dot right here, and this is an open, right? And so the function f of a actually equals, we'll call this, I guess, p, some value p instead, a different height. And then the last version, the one on the right, f of a just does not exist. That's not defined for anything. There's a hole in the function, right? And it's not redefined anywhere else. But in all three of these situations, right, regardless of how the function is defined at a, the limit of the function as we approach a in all three cases does in fact still equal L, because we don't care what happens at a, we just care what happens when we get really, really close to a. Okay, so in all three of these pictures, as x is approaching a from both directions, the function values are getting closer and closer to L. So the limit of the function equals L. Here's an example with some numbers. Okay, so we've got a nice simple function here, and we'll notice very quickly that the function is not defined at 1, right? If you try to plug 1 into that function, you get 0 over 0, and that's no good. So even though the function is not defined at that value, we can actually look at the limit to determine what the limit of the function, right, what the function is approaching as x gets to 1. Okay, so we can look at those numbers numerically. We can put a bunch of values into the function and spit out a bunch of answers. Look at a bunch of f of x's, right? Look at a bunch of y's, and kind of look for a trend. And we can see that as x approaches 1 from below, right, things that are smaller than 1, it looks like it's approaching 0.5. And then as x approaches 1 from above, numbers that are bigger than 1, it also looks like it's approaching 5, only we're getting smaller values, 4.999 instead of something a little bit bigger than 0.5. So based on those two, we would kind of make the educated guess that the limit is approaching a half. And in fact, if we look at the graph, we can see that it is in fact approaching a half. And we could even go so far as to look at the function reduced, because x squared minus 1 reduces to x plus 1 times x minus 1, right? And then these would algebraically reduce, and this would be equivalent, right? They're not identical functions, but they're roughly equivalent. They're equivalent everywhere except at 1, basically, but to 1 over x plus 1. And now if we look at this function and think about, well, what happens as x goes to 1, you just plug 1 into this function, you get 1 over 2, which is a half. Now with this new version, we're saying we're going to define this function differently, where instead of letting it be undefined at 1, we're just going to give it this other value of 2, right? That's what's happening with this piecewise function, is we're just saying, okay, we know the original function doesn't exist at 1, so instead we're going to redefine it for that point, and we're going to put a dot up there at 2. Doesn't really change things, right? Whether it's defined there or not, we still know that the limit is still 0.5. We can see it algebraically, that if because this one reduced, we can see that it's 0.5. If it didn't reduce, then we would have to look at the graph, or we would have to look at those tables of values. Okay, one-sided limits. Here is the definition of a one-sided limit. And pay close attention to it because it's really easy to miss. Right here, can you see the little minus sign above the a? That means the limit as x approaches a from the negative side, right? From smaller, from the left side. So x is approaching a from the left, meaning x is getting closer and closer to a, but the values of x are always going to be smaller than a, right? Less than a. And we say that that limit exists if we can get super close to L, right, as those values get super close to A. You'll notice that the only difference in this function, or sorry, in this definition from the original one, is that we're now saying x less than A. Rather, before we just said it had to be sufficiently close to A, and we didn't have this little extra kind of caveat that it also has to be less than A. So instead of saying we have to get close to A from both sides, we're just saying we have to get close to A from below. And then similarly, we can rewrite this entire thing and put a little plus. And when we put a little plus symbol there, that just means that x has to be greater than A. So we're coming at it from values above it. And everything's still the same. The definition is exactly the same. The only difference is here we would put x greater than A instead of x less than A. Okay, once we have these two one-sided limits, we have this nice definition that the limit of the function equals L if and only if the left-hand and right-hand limits also equal L. And it's an if and only if means it goes in both directions. If we know the limit of the function equals L, then we know both the left-hand limit and the right-hand limit both exist, and they must also equal L. But conversely, and this one's the one that's a little bit more helpful to us when we're trying to solve for these things, if we know the left-hand limit exists and it equals L, and the right-hand limit exists and it also equals L, then that tells us the limit in general exists and has to equal L. And that's normally how we use this definition to help us, but it does go both ways, right? It's an if and only if. All right, let's look at a visual example because this really helps drive it home. So here's some weird looking function, right, with all sorts of holes and gaps, right? It's got a step where it changes and where it's not defined, and all sorts of weird stuff is going on. And we're going to try and figure out what all of these limits exist. Okay, so let's take a look at the first one. If we take the limit as this function approaches 2 from below, that's what this means, right? We're approaching 2 from below. So we're coming at 2, but we're coming at it from smaller numbers. So we're looking at things here, right? Dot, 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 dot. Things really close to 2. And as we get really close to 2, where are we on the function? Well, if we're to the left of 2, aren't we on this function? And we're getting closer and closer to this point, which we're getting closer and closer to 3. Well, let me ask you this. What does g of 2 equal? Can we just plug 2 into the function and get an answer that way? Well, if you look at this graph, and I ask you for g of 2, hopefully you're all saying does not exist. Because these are two open dots, right? So there is no actually defined value for the function at 2. But we can see as we're getting closer and closer to 2 from the left, what's the height of the function approaching? 3. How about as we approach from the right, right? The plus means we're now coming at it from the right. We're getting things closer and closer over here, which means we're now getting closer and closer to that height of a 1. Okay, so the left-hand limit equals 3, the right-hand limit equals 1. So what about the limit as x approaches 2? What does the overall limit equal? And hopefully you remember from the definition that if the limit exists, the two one-sided limits have to exist and they both have to be the same number. So because they're different, this one does not exist. Okay, let's look at another example. How about we look at 5 from below, right? That negative means we're coming at it from smaller ones. So on the left-hand side, as we get closer and closer to 5, that means we're coming in this direction on the function, and it looks like we're at a height of 2. Okay, but what about when we come at it from above? Come at it from that direction. It's also approaching the same value. By the way, what does g of 5 equal? And according to this graph, you can all see that it equals 1, right? But if the right-hand limit is approaching 2 and the if the left-hand limit is approaching 2 and the right-hand limit is approaching 2, the limit itself also equals 2. It's just that simple, guys. Don't overthink it. There are ways where we can make this more complicated by trying to use the sigma delta definition to define these things and prove those things. It's not necessary here. We're just talking about limits as a concept, just understanding what they're doing and being able to evaluate them based on tables and pictures and maybe some simple algebra. Here's the solution all written up. You can look at that later. The last type of limit we want to deal with are infinite limits. An infinite limit is basically just a limit that ends up equaling infinity, either positive infinity or negative infinity. Okay, so when we talk about infinite limits, there are really two types of infinite limits that you'll come across. As far as you'll have a limit where x approaches a of a function and the answer ends up being plus or minus infinity. But there's another type of limit that is sometimes also referred to as an infinite limit, and that's the one where you take the limit as x approaches infinity of some function, and it's going to most likely equal a number. It doesn't have to. It could also go to infinity or negative infinity. But sometimes these are also referred to as infinite limits because we're looking at what happens to x as x goes out to infinity or to negative infinity. Okay, so two different types. In this particular instance, we're going to be looking at these where we're still approaching some number, right? Some a, and then the limit itself, the answer, ends up going to infinity or negative infinity. Here are some pictures of what this means. The picture on the left, figure 12, you can obviously see that as we approach a from both sides, the function is going up, right? It's getting taller. And so we are to assume that these just keep going, and they're getting asymptotically close to this vertical asymptote, and they basically just blow up to infinity. And then in this example, as we get closer and closer to a and on both sides, we can see that the function blows up to negative infinity, right? It just keeps getting smaller and smaller and smaller. And so the answer here would be positive infinity, the answer here would be negative infinity, and it's just that simple. Again, don't overthink it. Okay, so here's the definition of one that goes to negative infinity. You'll notice it's exactly the same as the one for positive infinity, only now the answer is that things are getting arbitrarily small. And here's an example of a function where this happens. Okay, we can do similar definitions for all of the left-hand and right-hand limits, right? As x approaches a from the left, from smaller things, it can go to infinity or negative infinity, and same thing from the right. So we can have one-sided infinite limits just like we can have one-sided regular limits. Here are some pictures of one-sided infinite limits. Here is the definition of the vertical asymptote. right? Whenever we have these vertical or these infinite limits, these lines at A are called vertical asymptotes because the function butts up right next to it, right? Gets asymptotically close but doesn't actually touch it. And we can find the equations of those lines very easily. The equation of a vertical line, if you don't remember, is always just x equals a constant. So whatever that number happens to be, in this case A, that's the equation of a vertical line. Here's an example. If we've got the function tan of x, which we know is sine over cosine, we know that this function is going to be undefined whenever the bottom is equal to 0, i.e. whenever cosine of x equals 0. So we can set cosine of x equal to 0 and solve, and we can realize that cosine of x gets closer and closer to 0 as x gets closer and closer to pi over 2, whereas when sine x gets closer and closer to pi over 2, it's getting closer and closer to, when x is closer and closer to pi over 2, sine x is just getting closer and closer to 1. And then you got to figure out, okay, what's happening as we go from the left-hand side. So numbers smaller than pi over 2, and if you don't remember how this works, draw yourself a little picture. All right, here's my unit circle. This is pi over 2, right? As I'm getting closer and closer to pi over 2 from smaller values, that means my angle is approaching in this direction. And as I approach in that direction, my cosine values are positive and my sine values are positive, right? I'm in quadrant 1, and that gives me a positive cosine, a positive sine, and so my answer is going to be positive infinity. However, when I approach from things bigger than pi over 2, that means you're coming at it from this direction, right? You have an angle that's bigger than pi over 2 and then you're backing it up. And when that happens, your cosine values are negative, your sine values are still positive, and that's why you get a negative infinity for that example. And then of course, if you graphed tan, you would see how that works. And this, you can see how we're getting positive infinity here, but negative infinity here, and then it repeats. Okay? Now, while we have this picture up here, this will remind us, before we looked at the limit as a function approaches a certain thing, and we got infinity and negative infinity. What would happen if we said, what's the limit as x approaches pi over 2 of tangent of x? So as we're approaching pi over 2, what happens to this function? Well, as we approach it from the left-hand side, right, from smaller values, we get a positive infinity. But as we approach it from the right hand, from bigger values, we get a negative infinity. So what does the limit actually equal at pi over 2? If one side goes to positive and the other side goes to negative, then we say the limit does not exist. Okay? So if you have a function that does this, then the limit goes to infinity. If you have a function that does this, right, on both sides, then it goes to negative infinity. But if you have a function that does this, or this and this, right, it goes up and down on either side, then both of these are do not exists. Okay, so when we're dealing with infinite limits, it's kind of the same rule as when we're dealing with normal limits. If the left-hand limit and the right-hand limit aren't the same, then the limit does not exist. And that works for infinities as well, right? If the left-hand limit is infinity and the right-hand limit is infinity, then the limit is infinity. If they're both negative infinity, then it's negative infinity, but if they're opposites, then it doesn't exist. Heck, you could even have a really weird function where here's my vertical asymptote, and the function does this, but then on this side it comes in and has, that should be a round, right? So it's not defined there. And so on the left-hand side, your left-hand limit is infinity, your right-hand limit is whatever this value is. Let's say that comes in at like positive 3. Well, then the limit of the function at that point, at this point A, is still does not exist, right? Because they're not the same. So again, Don't overthink it. It's very simple. Just take it from the picture, take it from the table, or do some simple algebra, but the bottom line is you're looking at left and right hand limits. What is it doing on each side of that number a? We don't care what happens exactly at a. If the left side and right side both equal the same, whether that happens to be a number or it happens to be infinity or negative infinity, then the limit actually exists at that point and we report it as such. If those two sides, the left and right, are different, then the limit does not exist. Okay, and that's all we need to know for just the basics of understanding limits.